So actually, in the last class, we were giving some idea about how to solve these partial differential equations using finite element. So let's start actually that what partial differential equations, what are the various means which can be solved. Some of them we already talked that we can solve that partial differential equation by finite difference one. So we solved one problems of heat transfer in a metal block, actually two-dimensional plane xy directions, and we wrote the program for that and complete formulations. But before starting this finite means elements, so I think I should give some idea that what partial differential equations are actually. So what partial differential equations? You have actually partial differential equations and multivariable function actually, and their derivative. So you have functions of several variables actually, and for that practically you need to create a computer model for that, and these are practically used in your various means all means of means engineering. Every problem most of the time is end up of partial differential equations because there is not a single function or property which depends only one parameter. Only thing for each of the calculation we simplify it for we just neglect that this doesn't depend on this parameter or that parameter. Based on that, sometimes we reduce it either to one dimensional because most of the time we are interested to that, and then it's converted to your ODE, which is easy to solve analytically also, right? So all the time we do some actually some similarity analysis, or let's say some dimensional analysis based on magnitude and all this. We generally neither neglect some other term by saying that it doesn't depends on these many parameters. So finally, we reduce all real equations to either one variable most of the time. Then if we want something to capture some means have some property which depends on more than one variable, then we end up with PDE actually. So in that case, it could be a two-dimensional, it could be a three-dimensional one, and obviously that steady state and unsteady state part, right? So these are the some. Now this is what I already told you just now here. So just arbitrary constants and functions relating them. So only thing is that how to solve these partial differential equations. So we consider some functions actually which can relate your all let's say your combined functions into more than one variables or two variables or three variables. Let's say you have 2D, two dimensions means then in that case you are adding two functions in that, and 3D practically maybe three, actually depends. So most of the time your functions are either space coordinate and or time, because these are the only two, space and time. And finally you will have a space, you will have some property. Actually property could be anything, it could be concentration, your pressure, or something else. Now this is, let's say this is your typical partial differential equations which have n number of x actually. Then you are having some functions there, because here you see in the denominator each time you are increasing some more number of variables, so second order term. Then again you will go to the, this would be a nth order one there. So based on that you can keep on adding derivative and complications and all this. So this is one of the PDE actually here. So here u is practically a function of x and y. And let's say you want to find its derivative with respect to x, so this would be a partial one. Maybe 0, may not be 0, we don't know that part actually. So this is some simple case actually. So in that case it is 0. Now there are several standard forms of equations actually. You can write a Laplace equation. Laplace equation practically anything which you can write in that form as del square of any function equal to 0, that is treated as a Laplace equation actually. So del square is called a Laplacian operator actually, and if it is del square of any function is equal to 0, this is being treated as a Laplace means equation only. So practically in your finite difference one, which we solve for metal block, so you have solved that Laplace equations in 2D plane, right? Correct?
Yes, sir.
Right. So and then you have another form of the equation that is called a Poisson equations actually. So Poisson equation is also given by this. So and then you have torsion the saw in the so these are some typical examples of, let's say, your equations actually. So Poisson equations is given. So here you see that you have the derivative second square, but it's not equal to 0 here, right? So that's called your Poisson equation. So what you have in your case that unsteady state your heat transfer in 2D plane or 3D is practically your Poisson equation without any generation term. Okay. Then you have flow through porous media is given by this. So this is again a sort of Poisson equations. Then pressurized membrane is given by this. This is also a sort of Poisson equation. Then again in electrostatic field is given by this equation. Diffusion equation is given by this. Then finally you have slow viscous fluid. You have a psi, that means the stream function, omega is the vorticity. So those are given this actually. The first one would be treated as a Poisson equation. Second one would be treated as a Laplace equation. So then you have in physics you have the Schrodinger equations. So this is also given. So this is again a you see here x, y, and z is 3D and with unsteady state. So that is again a partial differential equation. So practically you will have several, so these are some especially practically known, some special type of the equations in physics and engineering, and we want to solve them. So first one, let's say in our chemical engineering part, you want to solve for diffusion here. So in case this is not in a general format of the diffusion equation, this psi can be changed by any parameter. It could be any property which is getting diffused actually. So if you want to write it for concentration, so it will become here concentration C actually. Okay. If you, and this K would become your diffusion coefficient, fine. So if you want to write it momentum diffusion, then it would become something else. Momentum diffusion, what would it become? It will become rho into U, right? Because that is called the momentum, right? Mass into velocity is called momentum, correct or not?
Yes. Yes, sir.
So from that, if you are taking volume constant thing, and then it will become rho into U actually. So that can be the another one. Then you have wave equation. Wave equation again is given by this term. Then you have Kelvin-Gordon equation. That is again you have this. So C, H, and other represents the constant there. Now you have Helmholtz equation. So Helmholtz equation you might have seen in your first time, I think maybe in thermodynamics, correct or not?
Yes, sir.
So, but you see here, it looks like same is your also heat conduction problem with the with steady state condition, right? If I change this phi by your temperature T, so it will become T here, T here, T here, and this lambda dot phi would become entropy. Practically, if it is entropy generated, it will become thermodynamics, and it will be E dot the generation per unit volume. Then it become conduction thing, and that's so this time is zero, it means steady state operation, right? Correct or not? So in general
Yes,
form with this is the Helmholtz equation. Now it can be changed for various case studies, just like a Seychelles motion, it would be given by this one. So you need not to worry and by heart. These are some something that we want to know, that these are various type of equations. Let's say electromagnetic waves. So this that equation would be termed in this way. Then acoustic vibration, it would be termed by this way actually. Then finally, now what you have, all previous one, you have equations. Now there are the classifications of boundary conditions. That once you have the equations, is model formulation is being done. So over the time you will formulate the model, initially you consider everything, right? Because just like a mathematician, you want to say that I want to consider all the terms so that I can give the real picture of the system. But once you end up the model, you end up with the complications, just like all 3D plane, and could be you will have one property, you will have multiple property, and all of them in 3 dimensions. So the system becomes too much complicated. So finally, let's say you got some equation. Now you need to solve them. So you need boundary conditions, right? So boundary conditions can also be classified in the several categories. So first one you have here the Dirichlet boundary condition. So what does it say? That you know the function values at the boundaries actually, because we have solved, let's say previous one example is temperature equation. So let's say first temperature boundary condition. So you know the temperatures at the boundary, right? So it means your, and temperature was also your function only, main function. So that's called Dirichlet. You know the what is your function values at the boundary. That's called Dirichlet boundary condition. Next one is the Newman boundary condition, which say the derivatives are known at the boundaries, which means your flux boundary condition, right? In flux boundary condition, you know that the derivative k dt upon dx, right? And it was correlated by the some function, right?
yes,
Yes, sir.
yes, sir.
So those type of boundary conditions are called the Newman boundary conditions. Next is Cauchy boundary condition. Here you know both. You know the function values, you know the derivative also. You know the both the things. So that type of boundary condition is called Cauchy boundary condition. Other one is the Robin boundary condition, which is weighted combinations of Dirichlet and Newman actually. So what you have Dirichlet, you have function value, Newman, you have derivative, and these boundary conditions are that way that both the ends, the conditions are the such way that function plus your derivative is equal to something actually. So those are called the Robin boundary condition. Now next one is that you have the mixed boundary condition there. So in that case, at one of the end you know the temperature or let's say function, in other end you know the derivative actually. So that's called mixed boundary conditions. Means just like that. Let's say you want to solve it in heat transfer from a furnace or the reformer something. So the reformer inside you could have a pyrometer or a thermocouple there which is giving you the temperature. So you know the temperature at that. Let's say outside one, you know the what is air in outside, you know the temperature outside one. So practically you know the convective boundary condition, or let's say the whatever flux is coming there, you are balancing is equal to the convection heat transfer to the air actually. So one way you are having temperature, other way you will have derivative. That's one way. Or maybe anything that depends what can be measured actually. That depends, because it's practically all the time is not possible that whatever function is there we can directly measure. It's not actually. Just like pressure. So pressure in a container, okay, can be measured. You have the gauge, right? You can measure the pressure directly. Suppose you want to measure the velocity. So practically, except without you don't have any other meter which can give you the velocity. Correct or not?
Yes, sir.
Right.
Yes, sir.
So, and most of the time it cannot be used. So you have to go by some other means to solve it, right? So that depends. So now once we have all these boundary conditions, we have the equation. Now we want to solve them. So there are several techniques to solve your partial differential equations. First one is finite element method. So it works on global approximations and integral approach to differential equation. Finally, all of them are converting to a differential equation. All these, you have finite volume one, so most of the time is good for heat transfer of means operations where you want to have bulk heating or cooling type of thing. Then you have finite the difference. We have already talked about this actually. So you have point wise, you are the discretizing and means entire domain into your various grid points, and you can control your grid point, but those would be a equal size one, right? Then boundary element, the method is one, so this deals with integral equations rather than the differential one. So you discretize over the boundary only, or you are solving is only on boundaries only. Spectral method is another one, and orthogonal collocation. People also use that. So here, this works something faster, less computational time. So you have some collocation codes are there which can generate the points. I say the solve your equation only on those points, and then your answer would be perfect actually. So I will tell you only finite element one only. The rest of the part is means you can just see how they work actually. Sorry. So finite element one, actually you have this has a prominent position along the, because it works faster compared to other actually. So I will say that how does it work? Then the various means of this mass fire method includes generalized finite element method. Extended finite element method is given by XFEM. Spectral finite element is given as SEM. Mass free finite, because you are not creating any sort of mass again. So discontinuous Gillerkin's finite element one. And finite, I mean, element free Gillerkin finite elements another method. So a lot of work is being done on finite elements. Mean entire your system you are divided into several elements. Now you are solving in each of the element individually. So you are free to solve what method you want to incorporate in one of the element. You can change to element. So you have a lot of freedom in that particular part. So I will talk to you that Gillerkin's finite element method one. So this is what you have your finite element one that arbitrary have mean the geometry there, and you convert everything into some element. Let's say this is a beam. So you are so entire beam you have discretized into, or here you can see how many elements you have. One element is this, another element is this, and another element is practically entire beam. You have that divided into three elements. Fine. Now this is something thermal means analysis, just a block boundary. The flow system you have flow, heat convection, heat transfer. This is just a picture. The equation need to be put actually. Now this thermomechanical process and injection molding, and this is the rolling of your films. Actually, this is in case of metal formulations. Now, what is the generalized procedure actually? How does it work actually? The finite element, the element one. So any function, this in this case is given by this. Actually, you have this, and that need to be equated to zero. So what does it mean done? You are introducing an integral form of the equation, which is called a weak form. So you have practically a partial differential form. Now, which you are introducing some function in such a way that you are multiplying by that one psi integrated over the entire basis function of that. That's called, means you are making it orthogonalized, and finally the total the residue and all the points must be equal to zero actually. So what you have there, you are converting a strong format into a weak format. So I will tell what weak format is. After that, once it is converted to a weak format, it is being converted, calculated the residual at all the points. And once you have calculated that, then the residual must be equal to zero. So practically the residual means you are solving, finding the difference between left hand side, right hand side, taking by some basis function. And the difference, once you are solving a particular equation, your left and right should be equal, right? So practically, it in analytical solution it doesn't happen. So you want to choose some function that it is being incorporated in such way that it will give you the zero actually. So that's called a weighted the mean the residual the method actually. So this is again that how to discretize thing. So we will do only discretization in one dimension only. Practically, who's what about Khana? So discretizing the domain here. So practically, people make a lot of effort in discretizing the thing. You cannot. That is also a typical part, because a lot of work is being done just to discretize all the geometry properly actually. So this is most important part in the solving. So who works in really in CFD, Fluent and all this, they do a lot of work in discretizing mesh. Because once you have not the generated proper mesh size, you will be unnecessary end up of n number of equations which you don't need actually. So discretization is being done very carefully, just like I told you that wherever change is not much, you can take a bigger mesh. Where change is very appreciable, you can take a smaller mesh here. So you see here, these elements are bigger one here. As you are going to close to boundary here somewhere, you are getting a closer one there. So you will have again a different element in these particular points. So finally, let's say you have a function and which you want to discretize this, you want to calculate there. So this is being calculated at 3 points. Like let's say you have 1 point here, second point here, third point here. So I will tell what these nodal values are there and how does it being calculated. So once you know the values at different nodes and you can calculate in between values, I will tell what to do that. So we can skip this part actually. This might be confusing to you for time being. So so once actually you have generated something, the equation they end up with some integral format actually, and that need to be integrated. So integration, you already know the several methods are there for integration, right? You know the some of them how to integrate.
Yes, sir.
So you have the analytical integration, the numerical you have Simpson's 1/3 and 3/8 rule, right?
Yes, sir.
Yes,
Then
sir.
you have some other rule, trapezoidal rule also, correct? Then there could be many more, but all of them need a lot of points need to be put in between of that, and so that you can get accurate integration, right? So there are one more integration techniques here, the Gauss quadrature one. In Gauss quadrature one, the best one which works much more faster. There are many Gauss quadrature one. So Legendre's Gauss quadrature is being followed most of the point, and I will also talk on that. So what is being done in that particular case, the Legendre's Gauss quadrature one? Your function first need to be converted either 0 to 1 or -1 to 1. Okay. Once it is converted into this particular format, so every function first need to be converted. So that's is some extra work that need to be done. Once it is done, after that, what you need here, this is the Gauss quadrature way just to evaluate the integration. So it will give you, let's say, you have 2-point Gauss quadrature, 3 points also, 4 points also, 5 points also. So you can choose any number of points, and you will come to know that the best thing of that, once you have 3-point Gauss quadrature, if you are going to 3 to 4 and 5, your integration is not going to change actually. So and just evaluate this function at just 3 given points, and multiply by corresponding weights. So weights are given; those values are fixed. So so the evaluate the function at given points between -1 to 1, multiply by corresponding weight, add them up, because you need, if you want to calculate 3 points, you just add this 3 times. If add them up, you will get your exact integration, which is almost exact to your analytical solution. So I will show you one example of that. So this was thing I was talking to you actually that so I will say here just like that. So if you want to means integrate between let's say this particular curvature. So let's say you want to take 2 points. So practically 2 points you are taking this straight line, correct or not?
Yes, sir.
Hello. So this you do in your trapezoidal rule, correct or not? Trapezoidal rule you always go by this method, right?
Yes.
Yes, sir.
Means approximation. Now it depends how many points you want to take in between. So means let's say you want to take the points very close by. So let's say to in that case you are at the straight line means approximation would work well, because as far as you are on this curve, just like here. So if you have these points closer to these the previous one, you are just means the leaving this particular integration means you are this integration would be better than the previous one. Correct, but the only point is here is that this would be excess. You don't want this also, correct? So practically you want the point only here and only in this particular domain. You don't want outside your function. So if you are there, the inside one and close by point, you are getting better and better. Now, what this say the 2-point Gauss quadrature thing? This is say that objective. Then this function need to be evaluated two function x naught and x1 multiply by corresponding weight will give you the integration. So in that case, you are just actually minimizing the needs to calculate on several points. Just like in trapezoidal thing, in previously, if you want to integrate this entire area under the curve, so practically you may need the several points here. But that needs can be compensated by just this Gauss quadrature one. by evaluating the function at 2 points, multiply by this weight, and that's all. The integration is over actually. Now you have again, this is same, I think this is in the Gauss Quadrature one. Now here, this was thing we were talking, you calculate your function point. So first you have the converted your entire function to -1 to 1. That is the first part. Now these points x1 and x0 are given in between of that. So the derivation of that are also the given is purely mathematical one. So I am not giving to you all the derivation. I am just interested in how to use them only. Now let's say four unknowns to be evaluated. So let's say you have a function there. Now these are the four unknowns. Let's say c0 plus c1. You are calculating function x0 plus x1. You want to integrate from -1 to 1. So if you integrate that, you are getting 2. Let's say you have x there. You want to integrate that. You are getting it 0. X square, you are getting this 2 by 3. Then x cube, you are getting again equal to 0. So if this integration is exact for a constant, then you have first order, second order, third order function. So this is your first order function. This is your the second order function. This is your third order function, correct?
Yes, sir.
Hello? Now, once we know that, so we want to calculate what should be your C0 and C1. So let's, so if you want to solve the previous four equations, then you can solve it for x1, x1. So for weight factors, this you have given 1 here. So x0 is coming -1 by under root 3 is minus 0.57. X1 is given this minus. So this is practically you have calculated for 2-point Gauss Quadrature one, and these are the points. On this, you just calculate your function on this value and this value, multiply by weights. So weight has come just 1, and your integration would be exact. This is 2-point. Same way, this is what you did here, that if you want to convert your limit actually, so practically you have to convert your the limit from whatever you have, you convert it to -1 to 1. So that always needs some conversion points. So the limit conversion you might have done most of the time in your mathematics, but the still you can do that. That x equal to b, let's say you have here, what your function is. Now you want to make it here, you want to make it 1, right? X equal to b, you want to make it 1, and x equal to a, you want to make it again -1. Now you take the some other function, let's say in the form of the zeta. So zeta now changed from -1 to 1. Previously it was x, which is going to change from a to b. Hello?
Yes, sir.
Previous
Yes,
function
sir.
was function of the actually the x, which is getting changed from a to b. In between, it was a function of x. So you have the fx, and for that x equal to a, you have its function value something, and x equal to b, you have is the some function value. Now you have taken the another function f zeta. Now zeta is changing from -1 to 1. So let's say this is what you have there. This is -1. So zeta equal to -1. Your function is just a. F zeta is a only. And at zeta equal to 1, you have something. So you need to generate this one. So this would be your new way of change one. Your dx had been changed to minus b by a by 2. This is practically is your d zeta or dxd, whatever you say here. Dxd ko you can write in terms of zeta here. So don't get confused with that. This is zeta only, dxd. Fine. So your dx had been converted in terms of d zeta or let's say some other function. So this is where you have changed the limit actually. Fine. And this is how your x would change with respect to zeta. So x is given by this. So you can solve it, right? Can you solve this? How would you get x in terms of the zeta here? So you can write, let's say x equal to p plus m zeta, correct? Yes or no? Hello?
So can you please explain again?
Let's say a previous function was the x. Now you want to write is x equal to p plus, let's say some p plus m into zeta. Okay. Now you have two unknowns here, p and m. Zeta is the variable, right? So now you have two boundary conditions that let's say your x equal to b, your zeta is 1, right? And x equal to a, your the zeta is -1. Substitute those into that equation and you can calculate p and m.
Yes, sir.
To solve it, that can you able to get for this particular figure or let's say these particular boundaries, are you able to get your x in terms of this? Can you do it in let's say in 2 minutes? Your x is p plus m zeta and x equal to b, your zeta is 1, x equal to a, your zeta is -1. Can you find the constant p plus m, p and m?
Yes, sir.
आता है? Because you have
Yes,
two
sir.
equations. First one is b equal to p plus m. Next is a equal to p minus m, right? So if you solve them,
Yes,
you
sir.
will get p and m.
Sir, P is equal to B plus A upon 2 and M is equal to B minus A upon 2.
Same thing, right? So you will get this, right?
Yes, sir.
So your x is being converted in terms of the zeta just like that. Now you want, because you want to integrate that fx over dx. So your dx also, so x has been converted in terms of the zeta, which is this one. Now this you want to convert it now in terms of dx, you want to convert to dz. So you can differentiate this. So your the differentiation of this dx would be b minus a by 2 into your d zeta, correct? So that is
Yes,
your
sir.
dx. So
Yes, sir.
your integration from a to b fx dx is being changed now -1 to 1. This is new function, your f zeta multiply by your dx term. Now dx is now this b minus a by 2 into d zeta, right? So you got everything into -1 to 1 now, correct?
Yes, sir.
Now you can use your Gauss quadrature one. Now let's say here this one. So what your Gauss quadrature thing says, so so this, let's say you want to integrate a function here which we have converted previously, now -1 to 1. So let's say -1 to 1 you have a function. Now you want to integrate it. So you can write is for n points Gauss quadrature 1. So this is what I told you, the how to change the limit of any integration. So a to b fx dx, you want to convert it -1 to 1 dz into dz, gz into dz, and obviously there was some constant may or may not come, that we don't know actually. So you wrote here x equal to az plus b, and let's say x equal to a, your z is -1, x equal to b, z is the previous one only. We are talking about the previous one. So by putting these boundaries, you got a equal to this, your b equal to this, finally you got x equal to this one. From here dx you got this, so this is practically, yeah, this constant whatever is coming is your c only. That's what I wrote here, c. Now finally, after changing the limit here, you got a to b fx dx equal to minus b by 2 minus 1 to 1 gz into dz. Now this is what, for this you have an integration formula there, Gauss quadrature 1, where the integration can be changed to the summation sign. Summation of function values at various z multiplied by corresponding weights, and you will get integration without integrating it. So that's the, you can say, the importance or beauty of this particular method actually. Now we will take one example that how does it work. So let's say you want to integrate from 2 to 4 x4 plus 1 into the dx actually, right? So now you have here, we want to take for 3 points 1. So let the number of the Gauss points are n equal to 3. Your a is here 2, b is equal to here 4, correct?
Yes, sir.
So by doing that, if you want to write, because previously we did a Gauss quadrature, the conversion part. So if you will do the conversion, you will get this formulation that my b minus a by 2. And this would be, you want to integrate it by 3-point Gauss quadrature 1. So you can write this into 3 points. Omega 1, gz1, omega 2, gz2, omega 3, gz. So it means get the function value at z1 multiply by corresponding weight, function value at z2 multiply by corresponding weight. So these positions of z and weights are fixed to you. You need not to worry for that. Only thing, you should know a function and just calculate it. Now your x would be calculated by this from the previous one. So you will get here z plus 3. Now your gz would be calculated by this, because you have here z plus 3 to the power 4 plus 1. So this is your gz. Okay, because your this fine how this gz came.
Yes, sir. We are putting the value of x in the function.
Yes, yes. So you will get this. So you got the gz, correct? Now you want to evaluate it. So these are the Gauss points here. You have the tables for that. So if you want to calculate for 3 points 1, so you 3.1, your weights are given that W1 is 5 by 9, Z1 is minus root 15 by 5, W2 is 8 by 9, Z2 is 0, W3 is 5 by 9, Z3 is root 15 by 5. So these values are given to you. The tables are very well known. For 3 points, these are the points where you need to calculate the function between minus 1 to 1. And these are their corresponding weights. Multiply by them, add them up, you will get the integration here. So this is your the numerical the integration here. You are multiplying by weight. You are calculating the function at this given value of z1, and thus adding at all 3 points. So this is w1, fz1, w2, fz2, w3, fz3. Calculate that. You see here, I have just put at all points just to show that how accurate is it. So if you add all of them, your answer is coming to 100.4. Exact integration, if you want to integrate this, you will get x5 by 5 plus x. You want to change it from 2 to 4. And if you substitute that, your exact integration is this, analytical one. So you see your analytical one, the numerical integration by this 3-point quadrature is 100% same without any error. Correct or not?
Yes, sir.
Yes, sir.
However, in your other the numerical technique is not possible. Sometimes it could be, but most of the time it is not, right? So this is what all mean the integration can be integrated by 3-point Gauss quadrature without any doubt. Just calculate the function at 3 points. Only thing, you are just changing the limit. So that need your slight time. but your computation time is very low, right? Now let's say you want to integrate the double integration, because sometimes we end up with the double integration. We have two functions, one is this x, one is a function of r. So let's say this conversion part we already did. We have converted this function already from -1 to 1. So first one is already being converted from -1 to 1. Second one is also being converted to -1 to 1. Now we just want to integrate it only. So let's say we want to integrate this particular function x minus x cubed by 3 1. This if you want to integrate this, right? So if you want to integrate that, you will integrate this one by one actually, and then finally this would be your this is your analytical solution. Fine. If you want
Yes,
to
sir.
integrate this analytically, let's say the numerical one. Numerical one will say that now you have two functions. One is a function of x, the other one is function of r, right? So r1 I wrote as y. Now we want to use 3-point Gauss quadrature one. So x1 would also change from 1 to 3, and y1 would also change from 1 to 3. So first either you expand it for y or x is choice is yours. So I expanded it first for y. So y1 corresponding to the w1, y2 corresponding the
सर म्यूट है आपकी वॉइस. You're not audible to us.
Can you hear now? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Suddenly, I don't know what happened. The mic and video everyone turned off. So we were here. So the first one you have integrated means you have the expanded from for y. So y1 w1, y2 w2. Then you have y3 w3. Now each of these also would be expanded from 1 to 3 for x actually. So first line is for first function, second line completely for this function, and third line is for this. So in case of two functions, you are evaluating your functions at 9 points actually, and these are corresponding weights. So you know the already weights, you know the x1 y1, these are same points, whether you have x or y or p, it doesn't matter because your points are fixed. These are your points. These will not change no matter what function is. Okay, from -1 to 1 for 3 points. These are the points, your z, and these are corresponding weights. So if you will do that for this one, so if you will calculate your function, you already know the function because that was 1 minus of x square. So at the place of x, you have first point here, minus root 15 by 5. Next is 1 minus r square. So this is your first point, z1, multiplied by weights, w1, w1. So you have this. So you have put your functions, your corresponding weight, calculate that, you are ending up with this one. Now you see for this one, this is your answer from this one. Your exact answer is this. Fine. It's 0.77777. You have 100% consistency here also. If you will do that also, you will keep on 777 because I did 8 only here because you will the rounding off in this particular point. You can write in MATLAB up to 14 digit actually. I have not wrote till 14. So you will be now again you're 100% exact. Correct or not?
Yes, sir.
Yes, sir.
Right? So this way you are integrating your double integration part. So we will end here, and in next class we will talk about how to solve our equations of these ones which we were talking in the beginning, right? Fine.
Okay, sir. Yes, sir.
So we will end here. So you have seen this double integration and Gauss quadrature at least. So at least see them. How does it work? Take any function if you can solve them, so that you should have practice of that. Okay.
Yes, sir.
So
Yes,
we
sir.
will end here today. Yeah. So if you are free any other time, actually you just let me know because I want to cover up this finite element, and that probably we can end here because you have to prepare for exam because